Integrating trig functions is quite straightforward if you're already good at differentiating them. So looking at our differentiation rules, and these are the ones that are actually on our reference sheet, not the really simple ones with x, but the more complicated ones with f of x. If we know that differentiating the sign of some function gives us f dash x and the cos of the function, then if we have the exact same thing and we want to integrate it, we get back to where we came from. We get the sign of the function plus a constant. Similarly, if differentiating cos of a function gives us negative f dash x of the sign of a function. Now here, let's just do something cheeky. I'm going to rearrange this and then put it back. A perfect question would ask us to differentiate the negative f dash x sine of f of x. And if we had that, we would get the cos of a function, wouldn't we? But what if it's not a perfect question? Well, if it didn't have a negative here, then it would have a negative there. And you can see that just by looking at the fixed factor that you need to put in, if your question was positive, would end up over here. So we can write our rule down this way, just so that when we're integrating, we've got some rules to look at that have everything positive, and this is the one that will be negative. And I think you can see why that makes sense. These, by the way, are the ones that are on your reference sheet. So they're the ones that are good to be used to using. Have your reference sheet beside you while you're doing your practice questions. The last one, if we differentiate the tan of a function, we get f dash x out the front, and then we get sec squared of that function. So obviously integrating that exact same thing, we get back to where we started. So these are the formulas that we're using today. Now, an important thing, no calculation can cross an asymptote. And don't forget you've got asymptotes galore when you're looking at sec and cosec, and of course tan and cot. So anything that comes along there, just check what your bounds are and never integrate across an asymptote. Now for some examples. Here we need to find the area between a curve, the x-axis, and in this domain. Now the thing I'd do first in a question like this is draw it, because we want to make sure we know where the graph is above or below the x-axis, because if it dips above and below, we might need to add multiple areas together. And some of the integrals might be negative and we'll need to take the absolute values. So y equals sine of 4x has a period of 2 pi over whatever that number is, in this case 4. So that's the same as pi on 2. So drawing my sine curve simply, I know that it does one full rotation then every pi on 2. That means this point must be pi on 4. That's one of my bounds. And I need to go out the other way, the same distance. Whoops, a bit dodgy, but never mind. Good enough. And now I've got a simple little diagram here to show me that what I'm looking for is this area and this area. This integral is going to come out negative. So I could do it a couple of ways. I could find this integral, take the absolute value of it, find the other integral, add them together. But I could also use my knowledge of symmetry here to see that these are actually the same size. So if I wanted to just find this area and then double it, I'd get the exact same thing. And I think that writing that on my picture is a really good way of letting an examiner know what I've done. So now I can go ahead and find the area and say I want 2 lots of this section here. And now I'm just working with positive bounds, makes it a little bit easier. And I can put in my function here, which now I need to integrate with respect to x. Now, the 2 comes along for the ride, but when I go to integrate this, I need to stop and think about it for a second and realise this is not a perfect question. A perfect question would have the 4 out the front there. Now, you might like to think this step through in your head, or if you prefer to just write it out, it's probably just as quick and it saves you from making mistakes. What I really want to integrate is this, because on my formula sheet it tells me how to do it. What I get is negative cos 4x, and the 4 disappears. But I've now gone and changed my question. Remember that this 2 can be here or here, means the same thing. So if I had 2 but now I've got 4, I need to adjust for that. Half of 4 makes 2. So then my half comes along for the ride on the next line. And when I go to integrate this part, I just get negative cos 4x. Now I can write the negative cos 4x all in the brackets like that, or the negative, since it's just a constant, can actually come out the front. So whether you write it there or there, we're going to get the same result. Then I need to put my bounds in, pi on 4 and 0. And now I can sub in. I need my minus half out the front. And then I've got cos of, well, this will just be pi, minus the cos of 0. So that means I've got negative a half times, now cos of pi is minus 1, and cos of 0 is 1. So I get minus 2 times minus a half, which is actually just 1 unit square, or square unit. Now, a few steps there we can go wrong, but I think the main thing is make sure that your factor that you have out the front is going to work in with your integration, and then just take your time as you go through the steps. Remember that if you're finding area, you'll need square units. This example isn't an area question, it's just an integral that we need to find. So we know that tan of a function differentiates to make sec squared of that same function. So sec squared is going to integrate to make tan. So the first thing I want to consider here is whether or not I have a perfect question. What I would really like to integrate would be, if this is my function of x here, this part in brackets, then if I differentiate that, I get f dash x, which is 2. That's what I would prefer to have out the front. Because if I've got a 2 out the front, I can just follow the recipe here, and what I get is the tan of this function in brackets. Now, that's not what I've got. I was given a 3, not a 2, so I've changed it. So to change it back, I can get rid of my 2 by putting it on the bottom of a fraction out the front, and I can put in my 3. So that's my fixed factor. This is what I want to integrate, and now I can go ahead and integrate it. I need to just put my bounds in there. The constant comes along, square brackets, we get the tan of 2x plus pi, and oops, we need to put our square brackets in and our bounds. All right, now we need our constant, and now we have subbing in pi over 8. Well, doubling that gives me pi over 4. So I've got tan of pi over 4 plus another pi. That's 5 pi on 4. Minus the tan of, well, subbing in 0 here, I get 0 plus pi, so I've just got pi. Okay, on the next line, tidying up. Now I know that the tan of 5 pi on 4, that's just the third quadrant answer. That's exactly the same, in fact, as the tan of pi on 4, or 45 degrees. So that's 1. And the tan of pi is 0. If you want to put it in your calculator, you can, but I know that the tan of 0 is 0, and I know that the tan curve, y equals tan x, has the period of pi. So I know that the tan of pi is 0 just by thinking in my head about what that graph looks like. But by all means, feel free to use your calculator if you need to. So I've just got 1 here multiplied by this, and my answer is nice and straightforward. And I don't need any units because I'm just finding the value of this integral.